In lecture 28, we started to talk about being more quantitative with regards to how reactors that are behaving non-ideally can be described mathematically. And so we spent a lot of time in that previous lecture on this CSTR with both bypass and with dead zones in it. And we did the math in that lecture for a first order reaction. And then we also did some math regarding how to take some experimental data and use that to determine these parameters alpha and beta. Okay, so the first thing I want to do in lecture today is to then use the result from the end of lecture 28 and those values of alpha and beta to talk about a second order reaction, because the math is a little bit different for a second order reaction than it is for a first order reaction. Then I want to do another example where we use experimental data and look at a different type of reactor. So from the data, we have to figure out what type of reactor it is and then how we're going to end up describing it. And I think that'll give you guys a good opportunity for us to look at systems that are already really well known, but also for you guys to get some experience in looking at data and then trying to identify what is going on. Okay, so as I said a moment ago, we're going to start where the last example in lecture 28 left off, where we had this experimental data that was taking place in a reactor with a known concentration and a known flow rate. And essentially what we did was we derived equations where then we would plot the natural log of this CT0 minus CT over CT0 versus time. And that plot here in the bottom right would give you a slope and the intercept. And the intercept was equal to just the natural log of 1 minus beta. And then the slope was related to both alpha and beta. So what we did first was determine or read the intercept, determine beta, and then we used that to find alpha. And we found that alpha was equal to 0.7 and that beta was equal to 0.19. Now, let's use that, as I said a moment ago, for a second order reaction in the same reactor. So now we're going to look at A plus B goes to C plus D. And we know this reaction rate constant K1 is equal to 0.28 liters per mole minute. And Ca0 is 2 moles per liter. And the initial mole fraction of A is also 0.5, right? So we're going to feed stoichiometrically. So we're going to ask ourselves now to find the conversion and then compare that conversion to the value had this reactor behaved as an ideal CSTR. Okay, and we're going to follow a very similar path to what we did in the last lecture, where the first step is almost always, and in this case it is, solving the mole balance around the reactor. And then we're going to solve the mole balance here around this point that is starred, and we're going to end up with a final conversion. And then, as I said a moment ago, then we'll just treat this whole thing as an ideal reactor and compare the two. Okay, so just like we did in our previous lecture, we're going to start with the mole balance on the CSTR, right? And that's just in minus out plus the reaction term is equal to accumulation, okay? And if we do this balance on A, well, the inlet flow is just the volumetric flow rate that does not go through the bypass, or the thing that we call VS, multiplied by Ca0. And then leaving the reactor, we have the same volumetric flow rate, but now we're at the concentration leaving the portion of the reactor that is active, plus RA times VS, and that was equal to 0. Okay. Now we know from our reaction, we have A plus B goes to C plus D. If that's elementary, then of course RA is just equal to minus K1 times CAS, right? The same concentration that's leaving the reactor and the concentration of B that is leaving the reactor. Okay, so we can plug that into our equation, and we know that VS times Ca0 minus VS times CAS minus K1 times CAS CBS times VS is equal to 0, okay? Now, interestingly, in this problem, we're equimolar and we have a stoichiometry equal to 1. So no matter what we do in this problem, CAS is going to equal CBS in this particular problem. And that means that we can do this. We can say that this is VS times CA0 minus VS CAS minus K1 CAS squared times VS is equal to 0. Okay? And if we want to, we can actually rearrange this a little bit. And the reason that I would like to do that is because if you look at this, this is just a quadratic equation. So and I prefer my A terms, I guess, in the quadratic equation to have a coefficient equal to 1. So I'm going to write this as K1 times VS times CAS squared plus VS times CAS minus VSCA0 is equal to 0, okay? And now I'm going to divide through by VS, this the volumetric flow rate, and get K1 times the volume over the volumetric flow rate, CAS squared plus CAS minus CA0 is equal to 0, okay? And the next sort of batch of substitutions that we can make is that we know from our work last time that VS was actually defined as alpha times the volume, right? We have our 2-parameter system here. And we know that VS, the volumetric flow rate, is the initial volumetric flow rate times 1 minus beta. And so we can substitute those in here. And we get K1 times CAS squared times alpha V over V0 times 1 minus beta plus CAS minus CA0 is equal to 0. And we also know then, of course, that V over V0 is just equal to tau, right? Or equal to the residence time of our reactor. And because of that, we can simplify this just a little bit more and get that this is K1 times alpha times tau over 1 minus beta, right? And these are all going to be constants, times CAS squared plus CAS minus CA0 is equal to 0, okay? And this is already, like I said, a little bit different from what we did last time. Now, and that was really necessary because of that, where we have a quadratic here instead of a first order reaction where, you know, we had some term that was CAS times a product was equal to some things in the previous lecture. So we know for a quadratic equation like this, we can just use the quadratic formula, and that's, you know, CAS is going to be equal to, you know, negative B plus or minus the square root of B squared minus 4AC all over 2 times A, where this is A, this is B, and that's equal to C. Now, we know from our problem the value for each one of these, right? So A here is equal to K1 tau alpha over 1 minus beta. So K1 in the problem statement is 0.28 liters per mole minute times alpha, which was 0.7 times tau. And we are feeding to our reactor at 1,000 liters, and the flow rate is 100 liters per minute. So that's a tau of 10 minutes. And then that's divided by 1 minus beta, or 1 minus 0.19. So we know that our value for A here is equal to 2.4, and the units there are liters per mole. Okay. And now B, we can actually read right off of our plot. So B is equal to 1, right? So the coefficient in front of CAS is just equal to 1. And C here is just minus CA0, which is minus 2.0 moles per liter. Okay. And so if we solve for CAS, right, that just becomes equal to -1 plus or minus the square root of 1 squared minus 4 times 2.4 times minus 2.0 divided by 2 times 2.4. And we can calculate a concentration for CAS, which is equal to 0.72 liters per mole. Okay. And so the quadratic here made the math a little bit different, but we still did the same procedure that we did in the previous lecture, where we used our mole balance to find this concentration of A leaving the active part of the reactor. And now to get the final conversion, we need to do a balance around that mixing point that I showed a minute ago that we've done before, right? That one. And just like before, the mass balance here is just in minus out is equal to 0, right? Because there's no reaction term, we're operating at steady state. And just like in the last lecture, we have 2 streams in, right? One at the through the active part or leaving the active part of the reactor, or VS times CAS, then plus the bypass. So VB times CA0, and then minus the concentration of A that's leaving that junction times V0, or leaving the actual reactor times V0 is equal to 0. And just like we did last time, we can start to make a few substitutions. So we know that VS, again, is V0 times 1 minus beta times CAS, plus the bypass volumetric flow rate, which is just beta times V0, minus CA times V0 is equal to 0. And so all of these initial volumetric flow rates are going to cancel. And so then we get 1 minus beta times CAS plus beta minus CA is equal to 0. And so we get a final expression then for CA, right? So CA just equals 1 minus beta times CAS plus beta, okay? And in this case, right, that's 1 minus 0.19 times 0.72. I apologize. I made one little mistake right here. I'm sorry about that, right? I dropped the CA0. I'm sorry. Right, CA0, that's also beta times CA0. And I'll give you guys a second to catch up here, in case you have to go back and make changes in your notes. Okay, and then we can find that the final concentration of A then is equal to 0.97, leaving our real reactor. Okay, and the last thing we want to do then is to find the conversion, right? Conversion is 1 minus CA over CA0, and that's equal to 1 minus 0.97 divided by 2.0 moles per liter, and that is equal to 0.52. Okay. Okay. All right, other than that little mistake here where I had dropped CA0, does anybody have any questions about this? Another note is that we also could have solved this for conversion explicitly at the beginning. We could have actually defined, if we wanted to, an intermediate conversion here, right, that we would call like X star. And then we could have actually gotten this equation from here in terms of X star, and then also had a quadratic and solve for X star. And in the next example, I'll actually do that. So you guys see it done both ways, where you see the concentration solved for, and then you have one where we'll actually do the substitution for that intermediate conversion. Okay. All right, so then we were asked in the problem statement, what would have happened if this were an ideal reactor, or how does it compare? Well, of course, for an ideal reactor, we have the same mass balance, right? In minus out plus reaction is equal to 0, or FA0 minus FA plus RA times V is equal to 0. And again, FA0 minus FA0 times 1 minus X, then minus K1 times CA times CB is equal to 0. Right, I made two substitutions here. One there, and then I put this there times the volume. And then I'll insert these also as functions of conversion. So we do know that FA0 minus FA0 times 1 minus X is just FA0 times X. We've done that before this semester. Then that's minus K1. And both A and B are CA0 times 1 minus X. So that's CA0 squared times 1 minus X squared times the volume. And that's equal to 0. We then also can write FA0X as CA0V0X minus K1 CA0 squared times 1 minus X squared times the volume is equal to 0. And we could divide through by CA0 times V0, and we get X minus K1 CA0 times 1 minus X squared times tau is equal to 0. And then we could rearrange this if we wanted to. And I did it this way. You could FOIL this out if you wanted and do this as a quadratic. I chose to actually write it instead as X over 1 minus X squared minus K1 CA0 times tau is equal to 0. And I basically just use solver for this. So we know X over 1 minus X squared minus 0.28 liters per mole minute times 2.0 moles per liter times 10 minutes is equal to 0. And so the conversion then is equal to 0.66, which is significantly higher than we had for the non-ideal case, right? Where the conversion was equal to 0.52. So you'll see that in this particular case, I mean, we have about a 20% drop in our conversion from the ideal case to the real case, where we have bypass and dead zones. Okay, and it's just another example of how for how these non-ideal behaviors really negatively influence conversion. Okay, so before we solve another example problem, does anybody have any questions about this one that we worked on? Okay, if not, let's do our final example. And here it is. So this is actually a problem in Fogler 5th edition, and it's problem 18-17. And we're given this figure, and we're told that there's a 2,000 liter reactor that needs to be used to carry out the liquid phase second order reaction. A plus B goes to C. A and B are to be fed in equimolar amounts at a volumetric flow rate of 1,000 liters per minute. Ca0 is 2 molar. K1 is equal to 1.5 liters per mole minute. And a tracer experiment was carried out with A, and the plot to the right was observed. So the first thing that we need to do is to come up with a model that would describe the data, and we'll come up with a 2-parameter model again. And then we'll do some math and we'll solve for the final conversion. Okay? So what I'd like to do is open this up to you guys and think, what do we know about the system based on the figure? You know, what kind of reactor is it? Maybe that's the first place to start. So maybe one way to start thinking about this is, if you look at this, right, you have a reactant that has this sudden jump at one residence time. What type of reactor do we normally have that does that?
PFRs, we don't usually have to worry about mixing as much. And so I feel like there would be less like like variance in the residence time because of that.
So how in a PFR do we assume everything moves through the reactor? As a what? It's in the name.
Like a plug.
As a plug, right?
Okay.
So you have something that's moving through at, let's say right here, and it's just traversing its way down the reactor over time, right? And so if you fed that to the reactor and you had some behavior that was operating that way, right, you would see this sudden jump at the end, right? You wouldn't see anything, and then boom, all of a sudden that happens. Okay, so I'll give you guys that. We know that our model is going to have at least one plug flow reactor in it. Okay. All right, so I'll draw that. I'll draw a PFR. So then let's go back to this. So we use this jump to tell us that it was a plug flow reactor. And this F of T is just a normalized flow. So this just tells us that, here we have all of it. So when I look at this, I want to look at this. So this basically tells us, like right at time equal to 0, we already have half of the flow coming through. And then we have something that follows at some residence time. So what else do we have here where we would instantaneously have flow?
That would just be another plug flow reactor, maybe?
Could you have a plug flow reactor, though, with a residence time equal to 0?
I'm pretty stuck on this one. I'm trying to see.
That's okay. At least you're talking through it, right? That's part of solving the problem. What about somebody else? What else could we have?
I don't know if this would be instantaneous, but I was thinking like a short circuit or bypass.
Bypass is correct.
Okay.
So absolutely a bypass could explain that behavior. Now, whether, our definition of instantaneous or whatever, fine. I mean, you're right. It would be offset maybe by some slight time, but a bypass in theory does exactly that in our flow diagram. So, we would have, let's say you want to flow into the PFR, right? Well, what you would have is some portion that does this effectively. And so we have, let's say, some initial concentration, right, of our species here. Or I guess we're talking about the tracer first, right? And at some initial volumetric flow rate. And again, we have some portion of the flow that goes through bypass, and we'll also just call that beta times V0, just like we did before. Now, we have a real volume, and in a real reactor, right, you don't bypass external to it. So if you have bypass in a PFR, you almost naturally have to say that you have dead volume. So we'll also have dead volume. And V sub D is equal to the volume times 1 minus alpha, which means our active volume, which we'll call V1, is alpha times the volume. And so here, just like we had for the CSTR, we have a 2-parameter model where we've defined 2 variables, alpha and beta. And now our task here first is to try to figure out what those 2 parameters are. Okay, so let's go back to the figure. I know what beta is just by looking at this figure. Can anybody else tell what that is? So based on this, what portion of the flow do you think short circuits?
Half of it.
Half of it, right? That's how F of T is equal to 0.5. So we can actually read this directly from the graph, that is equal to 0.5. And that's a really good way to do this. When you see a plot that is either this F of T, but you also could have a concentration versus time, and it wouldn't be bound necessarily by 0 or 0.5. Let's say that this were, 1 and 4 or something, right? You also would know that you could solve, in that case, for beta would be 1 over 4, right? And so, the F of T that the book uses picks those bounds as 0 and 1, so everything's normalized. But you don't have to do that, and we won't necessarily do that all the time. So from this particular plot, absolutely. So we have 0.5, 1. We can read directly off the plot that beta is equal to 0.5. Excellent. So now what about alpha? How are we going to find alpha? Well, the most natural way to find alpha is somehow from this volume. And we know that to find alpha, the only other piece of information we really have at our disposal then is the residence time here, which is 2 minutes. So if we think about this, how do we relate the residence time to the alpha value? And to do that, we know that the residence time is going to equal to V1 over V1, right? Where that's the volumetric flow rate that doesn't go through the bypass. Well, this is just equal to alpha times the volume divided by V0 times 1 minus beta, right? Just like when we did this in the CSTR case. And V over V0 is just the residence time. So maybe I'll call this tau 1 to make that a little bit more clear. And then this just equals alpha over 1 minus beta times tau for the reactor. And so if I want to solve for alpha, so alpha then just equals tau 1 over tau times 1 minus beta. And from our data, we know what tau 1 is. We read that off the plot, so we know that that is 2 minutes. And also, from the data that we're given, we can calculate tau for the reactor, where we're at 2,000 liters, and the volumetric flow rate is 1,000 liters per minute. So the residence time here as well is equal to 2 minutes times 1 minus 0.5. And so if we look at this, we can find alpha equal to 0.5. So now we have beta, and now we have alpha. Okay. So now that we have used the experimental data to solve for alpha and beta, let's solve for the conversion in the reactor. And we're going to do the exact same thing that we've done previously. First, we're going to do a mole balance on here, the reactor itself, and then we're going to do one here at the mixing point. It'll follow the exact same procedure as the CSTR. And so in a plug flow reactor, we know that DFA dV is equal to RA. And in this case, we were told that our reaction is A plus B goes to C, okay, in the liquid phase. All right, so we have A plus B goes to C. And if it's an elementary reaction, that's just minus K1 times Ca times Cb. And for this process, right, if it's isothermal and we have a liquid phase reaction, we know that there's no change in the volumetric flow rates. And so because of that, Ca just equals Ca0 times 1 minus X. And also Cb, they're fed in an equal molar mixture, right? So this is Ca0 times theta B minus the stoichiometric coefficient of B over A times X. And in this problem, that just becomes Ca0 times 1 minus X as well. So let's go ahead and plug in our conversion into this expression. So DFA, of course, in terms of conversion is minus FA0 times dx, right? So minus FA0 dx dV is then equal to minus K1, and then inserting these expressions that we have for the concentration of A and B, that's just Ca0 squared times 1 minus X squared. And we can reorganize this equation just a little bit, and we get dx over 1 minus x squared is equal to K1 times Ca0 squared over Fa0 times dV. And of course, this is also just equal to K1 times Ca0 over the volumetric flow rate times dV. And so then we're going to integrate this from 0 to X star, right? The conversion leaving the active part of the PFR. And then we are going to integrate that from 0 to V1, okay? And, or the active volume in the reactor. So when we do this, right, we get on the left-hand side, this is 1 over 1 minus X evaluated from 0 to this thing that we called X star. And then that is equal to K1 times CA0 times V1 divided by our volumetric flow rate. And we can now introduce alpha and beta into this, right? This just becomes K1 times CA0 times alpha volume divided by V0 times 1 minus beta. Okay. And so the left-hand side here becomes 1 over 1 minus X star minus 1 is equal to K1 times CA0 alpha V over V0 times 1 minus beta. And then this is actually just X star over 1 minus X star. You just do a little bit of reorganization, and that's equal to the same thing here, CA0 times alpha V over V0 times 1 minus beta. And we can plug that in. So that is 1.5 liter per mole minute times CA0, which is 2.0 molar, times alpha, which was 0.5, times our volume, which was 2,000 liters, divided by our volumetric flow rate, which was 1,000 liters per minute, times then 1 minus beta. Okay. And so this whole thing on the right-hand side just equals 6.0. And from here, you get that X star equals 0.86. Okay. So we have 86% conversion coming out of the active part of the reactor. So now we have to do a mole balance at that intermediate, or at that sort of mixing point that comes at the outlet. And of course, that's just in minus out is equal to 0. And again, we have two streams in, one from the active part of the reactor, one from the bypass, and then the other one leaving. And so this just becomes V1 times CA1 plus the bypass, right? VB times CA0 minus V0 times CA is equal to 0. And so this first term just becomes V1, and this is what's leaving the active part of the reactor. Well, of course, that's just CA0 times 1 minus X star. And that's plus the bypass times CA0 minus V0 times 1 minus the total conversion that we're after. And that's equal to 0. And I said I would do this example a little differently, right? Explicit in terms of the conversion we're looking for, right? So these CA0s are going to cancel, right? And in order to do that, I have to actually put all the CA0s, right? This is CA0 times 1 minus X, right? So those go away. And so now we get this expression that's just V1 times 1 minus X star plus VB minus V0 times 1 minus the conversion is equal to 0. So now let's pick a look on these V0s just a little bit. Well, V1 we know is V0 times 1 minus beta times 1 minus that intermediate conversion plus V0 times beta minus V0 times 1 minus X is equal to 0. And now again, all these V0s are going to cancel. So those V0s all go away. And we're left then with this expression where 1 minus beta times 1 minus X star plus beta minus 1 plus X equals 0. And I just distributed the negative into here. And so we get this expression then for the actual conversion. It's 1 minus beta minus 1 minus beta times 1 minus X star. Okay. And if we substitute the values that we have here, that's 1 minus 0.5 minus 1 minus 0.5 times 1 minus 0.86. And so our actual conversion that we achieve in our reactor is equal to 0.43. And so here's a great example of how we had a very, very negative effect. And you could have expected that because half of it bypasses, you end up with half the conversion.